Now this is Euler's equation. We have our imaginary fluid particle, element, whatever you want to call it here, which obviously doesn't exist in real life because fluid is a continuum. But on this fictitious particle, this cube, there are two types of force acting upon this. The surface force due to the action of the rest of the fluid, and body forces due to the external factors such as gravity. Now during this, you note the relationship between pressure and density. That's quite an important thing. So the total force here, the resultant force, is that of the surface force and that of the body forces, which the body forces are here, which is the negative gradient of the pressure integrated over its volume. Now the density forces are here, which is the integral of the density force over its volume, which gives this equation here, which noting that the rate of change of linear momentum is dp by dt equals the integral of b of the density of du by dt dv, which gives this here. Or when we collect terms and do a little bit of juggling, we get this. And since this applies to any region of fluid B, the usual assumptions of smoothness enable us to write the equation as this, and this is Euler's equation for an inviscous fluid. It's straightforward so far. Now here's an example. A flow of constant density, a constant density fluid velocity field is given here as such, and the body force is F equals 2yi. And to find the expression for a pressure at a general point xy, we use Euler's equation here, and we're plugging in these values here and going through the solution, should I say, plugging in the values to obtain the solutions. And the x component is this. Since density is constant, this integrates to this. Now the y component likewise is this. So the pressure at x and y in time t is this, and this is the final solution. This should be pretty straightforward to follow. We're just plugging in values and doing the juggling. And that's the Euler's equation in fluid dynamics.